NASA's Dragonfly mission, a flying rover designed to explore Saturn's icy moon Titan, 1.5 billion kilometers from Earth, relies on a critical but scarce resource, plutonium-238. This man-made isotope, with just 4.8 kilograms powering Dragonfly, is nestled between thermocouples in the rover's drone-like structure. The United States is running dangerously low on this vital nuclear fuel, a shortage that has already impacted missions like Europa Clipper, which was forced to use solar panels despite the low-intensity light in Jupiter's orbit. Many at NASA's Jet Propulsion Laboratory believed Europa Clipper should have used plutonium-238, but with supplies dwindling, it was reserved for missions like Dragonfly. This scarcity is a significant problem, as plutonium-238 is essential for powering ambitious deep space exploration. So, what can be done to address this shortage? The issue hasn't always existed. During the Cold War, the global race to build nuclear arsenals inadvertently produced valuable byproducts. In the 1950s, secretive facilities worldwide began creating fissile plutonium-239 in large quantities for weapons. The United States, Russia, the United Kingdom, France, China, and Israel all developed nuclear warheads, and while refining weapons-grade plutonium, other isotopes, including plutonium-238, emerged. Considered waste by the military, NASA saw potential in this byproduct. Unlike plutonium-239, which sustains chain reactions for bombs, plutonium-238 emits steady, reliable heat without the risk of fission. This heat, generated by its slow radioactive decay, can power spacecraft in the darkest, coldest corners of the solar system. Plutonium-238 is created by bombarding elements like Neptunium-237 with neutrons in a nuclear reactor. Differing from plutonium-239 by just one neutron, it transforms from a tightly controlled substance into a remarkable material that glows red-hot for decades, with a half-life of 88 years. This heat can be converted into electricity, making it ideal for space exploration. Since its discovery as a power source, plutonium-238 has been critical to NASA's missions. It powered the Apollo lunar experiments, the Voyager probe still transmitting from interstellar space, the Cassini mission to Saturn, and the Curiosity and Perseverance rovers on Mars. Now, Dragonfly depends on it to keep instruments running in Titan's extreme cold and to enable powered flight on another world. The shortage stems from a 1988 decision to halt weapons-grade plutonium production in the United States, a move driven by aging reactors and an already massive nuclear arsenal. While this was a positive step for global safety, it crippled plutonium-238 production, as the Savannah River Site's K reactor, a key facility, was shut down. The situation worsened in 2010 when the US stopped importing the isotope from Russia. By then, NASA was rationing a shrinking stockpile. In response, NASA and the Department of Energy restarted production in 2011, but the current output of 550 grams per year is far below demand. With plans to scale up to 1.5 kilograms annually still insufficient for missions like Dragonfly, which alone requires 4.8 kilograms. Alternatives to plutonium-238 have been explored, but none match its unique properties. In 1959, NASA tested polonium-210, which generates 140 watts per gram, but has a half-life of just 138 days, losing half its power before a spacecraft could reach Mars. This makes it impractical for long missions. Space exploration demands a nuclear fuel with a half-life between 15 and 100 years, emitting only alpha particles for easy shielding and high energy density. Of nearly 2,900 radioisotopes, only 20 to meet the half-life criterion, and fewer satisfy the radiation requirement. Alpha particles, like those emitted by plutonium-238, are helium nuclei traveling at 15% the speed of light, carrying 5 megaelectron-volts of energy. They generate heat by colliding with electrons and nuclei within the fuel and are easily stopped by light materials, protecting both spacecraft instruments and personnel. Curium-244, another alpha emitter, was considered due to its high power density 5 times that of plutonium-238 and stable oxide form. However, its 18-year half-life is on the shorter side, and it emits higher levels of gamma and neutron radiation due to spontaneous fission, requiring heavy shielding that adds weight and complexity. Producing curium-244 is also challenging, as it involves plutonium-239 capturing multiple neutrons and decaying. A costly and impractical process with no existing infrastructure for large-scale production. The fuel must also withstand extreme conditions, such as launch accidents or atmospheric re-entry. Plutonium-238 is used as plutonium oxide pellets encased in iridium shells, chosen for their strength and ductility at high temperatures up to 1000 Celsius. This design ensures safety, as demonstrated in 1967 when a plutonium generator from a failed weather satellite launch was recovered from the Pacific Ocean, reprocessed, and reused. Similarly, during Apollo 13, a generator sank intact to the ocean floor, safely containing the material. Another candidate, gadolinium-148, has a 75-year half-life and emits only alpha particles, but its production requires expensive particle accelerators, making it NASA's options are to increase plutonium-238 production or improve the efficiency of its use. Current radioisotope thermoelectric generators (RTGs) rely on the Seebeck effect, where a heat gradient across two semiconductors, one with electron charge carriers, the other with electron holes, creates an electric current. These semiconductors typically lead telluride for the N-type and a tellurium silver germanium antimony alloy for the P-type, must be thermally insulating to maintain the gradient but electrically conductive to maximize current. Such materials are rare, as good electrical conductors like copper are also good heat conductors, while poor conductors like iron are poor in both. RTGs convert heat to electricity at only 6 to 7% efficiency, wasting most of the fuel's energy. NASA explored the Stirling cycle, which compresses and expands gas in a sealed system to convert heat into mechanical energy, driving a generator. Stirling engines could achieve up to 30% efficiency, reducing plutonium needs by a factor of 4. However, in 2013, NASA cancelled the Advanced Stirling radioisotope generator project due to technical issues with the piston, underestimated costs, and budget constraints. This leaves increasing production as the primary solution. Production restarted in 2015, using Neptunium-237 from Cold War stockpiles stored in Indiana. The process involves 3 facilities across different states. At Oak Ridge National Laboratory, neptunium is distilled, precipitated into a metallic powder, pressed into pellets, and encapsulated in aluminum for irradiation. In a nuclear reactor, Neptunium-237 absorbs neutrons to form unstable Neptunium-238, which decays into plutonium-238 via beta decay. The neutron flux and irradiation duration are carefully controlled to optimize conversion. After irradiation, the material is dissolved in acid, and plutonium-238 is chemically separated, purified, and converted into ceramic oxide pellets at Los Alamos National Laboratory for use in RTGs. Despite the process being well understood since the Cold War, scaling up is challenging. Only 2 U.S. reactors, the high-flux isotope reactor at Oak Ridge and the Advanced Test Reactor in Idaho, can irradiate targets effectively, and both are in high demand for other nuclear research. The conversion process is inefficient, with 1 gram of neptunium yielding just 0.5 grams of plutonium-238. Neutron bombardment can destroy neptunium-238 through fission, and even when plutonium-238 forms, it can be further radiated into unwanted isotopes. Achieving 85% purity is difficult, as separating isotopes differing by 1 or 2 neutrons is nearly impossible. To maximize yield, targets are irradiated in short, high neutron flux cycles, allowing cooling periods to let byproducts decay, but this is time-consuming and resource-intensive. Current production of 550 grams per year is set to increase to 1.5 kilograms, but even this won't meet demand. Dragonflies for 0.8 kilograms will take 3 years to produce, limiting other missions. The European Space Agency, particularly France with its nuclear infrastructure, is exploring its own production. Plutonium-238 could also power lunar missions, especially in permanently shadowed craters where solar power is ineffective. These regions, rich in water ice, require reliable energy for rovers, landers, or habitats during the long lunar night.